In this lecture, we will talk about stream, path lines, strike lines, and the whole idea behind this is if I take back my airplane, right, I want to know how that particle actually is moving across my plane over time. I want to be able to draw the lines. I want to be able to draw how the flow looks like. So slowly we are building upon the fact that we are slowly going to start to understand how the flow looks like, to be able to draw that flow around an airfoil, around the car, around the plane, around to whatever. Okay, so to start with this, consider the following case. Uh, First of all, we talked about this. We talked about considering the case that you have a car, let's say, you have air flowing around this car. And because you have air flowing around this car, just give me a minute. I have air flowing around this car. You're going to have some velocity around there. If I move at a distance, significant distance, I can say my airflow is uniform around, far away from the car itself. But when it's a get close by, then in the near distance, you have what we call the boundary layer that we talked about for a couple times now. And the boundary layer, so you can say, that the velocity of the air is no longer, the speed of the air is no longer uniform here. It becomes uniform as it moves away from the surface. Okay? So in the case of an airfoil, as for an example, let me draw the airfoil over here. If we had an airfoil, in the case of the airfoil, you can assume that you're coming at a uh, uniform speed, but then when you're coming here, it's not so much uniform, and your air is, the streamlines are going to look something like this, and you keep moving on, and then it looks something like this as you move along, and then what's going to happen is eventually, as you go further away, they become basically uniform. Um, and then here, the same thing at the bottom, it's not going to be that uniform. It's not going to be that uniform, but as I move away from my airfoil, I can assume that these are uniform lines. So what we are saying is what you have on this segment here, you can say all the stream of my airfoil there, U infinite, is uniform. You could say everything happening here is uniform. Everything away from the airfoil is uniform. Everything far away from my airfoil, all these are uniform streams. However, as you're getting close to airfoil, what you have where is a no slip condition, you can see that it's not that uniform because you have a boundary layers that develop, right? Anything below the boundary layer is not uniform. Anything above that is uniform. Okay, so that's important. Uh, and then you have three type of cases. You have a case of one-dimensional flow. One-dimensional flows mainly internal flows. They're internal. You can think, as I told you last time, maybe pipes, heart valves, the anything that goes inside a tube that will be one-dimensional. Okay, because you really doesn't have enough space to, if it's going fast enough, it's not going to have enough velocity to develop velocity in the opposite direction, in the radial directions, as for an example. Okay, two-dimensional flow may look something like this. In the case like in the wind tunnels, you have this very often, where you have the flow and then it's coming out. As you can see, as it expands, the only way the flow could expand is if it's actually moving in the opposite directions. So you may not be able to appreciate this, but these flows right here, these arrows, are actually going in this direction. Okay, so this is kind of like, so because the arrows are no longer horizontal, they're going to have two components. They will have a vertical component and a horizontal component. Okay, and this may be this will be the case of the airfoil, right? If I have an airfoil, you can expect the airflow here will be 2D, two-dimensional. Now, in the real life, what we have the case of three-dimensional flow. And it's almost impossible to study three-dimensional flow by hand. You cannot do maybe some very simple hand calculation approximations, but mainly you need to have wind tunnel uh, or computational fluid dynamics, what we call it and we do. So what happens around this is lots of bounded vortices, and those vortices are going to create that these are trailing vortices, these are leading vortices, and they create lots of headaches for us many times. Okay, so this is a three-dimensional model in which it may look something like this if I was trying to model this in the computers. Okay, so we will talk about some approximations for 3D, but mainly how we can just model the 3D approximate and the two-dimensional, and maybe using some factors involved with that. Okay, so with that said, let's change the colors here. Let's talk about what's a path line. So if I have a fluid, right, a small fluid particle, and that fluid particle is moving with time. Okay, so this particle is moving in time. So where at time t1 0 is equal to here, at time t 1 is equal to here, at time t end is here, maybe at time t2 is over here, and then having that many times, what I will get is the path line that the particle has moved. Okay, so that's the case of the airfoil, right? I got the airfoil. The only reason I know that my flow actually is going to look something like this is because I am assuming that I'm going to have a particle, and that small particle is the ball, is the tip of my pen right now, and I'm just moving. So you have that particle that moved from here, and it's moving across this path line. That's what it's called, a path. Okay, and just you can assume that that's what it's going to be doing. Okay, then what we have is something we call the streak line. The streak line is nothing else, something that's streak line is a little bit different. It's similar but different. So consider this case. Let's suppose I have a particle A, and this particle A just comes and moves over here. Then I have it's moving here, it's moving there. Let's suppose I have another particle. This particle is also moving and is doing something like this, is there, and this is all at time 1, let's say. I have another particle that's actually doing maybe something like this, and this is this. And so what I would do is, the streak line is how many times the particle has moved in the same spot. Okay, so I could say the streak line will look something like from here to here to here, because at time 1, this is where the particles have moved from. It's a streak. You see, they're leaving like a trace that will go from this point to this point, this point. So it's a likelihood of the particles moving across that line. That's the way we can see it. Okay. And so the other item that we want to talk is the streamlines, right? The streamlines are these are not the path lines. Okay, path line is where the particle is moving. Streamline, I want you to think like if for one instant here, I have a vector velocity, and I'm drawing this tangential vectors that represent the tangent of that curve at that point. Okay, so now I have that. So basically, the streamlines help me to understand how is the flow around an object, but it also tells me the velocity gradient involved with that. And very nice little derivation is this small equation that I strongly encourage that you pause these videos, you take your definitions, you write them down. Um, and this is a very, 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 very important equation, and we will be using it a lot. If you're working two-dimensional flow, you're only going to have mainly dx du is equal to dy dv v, where this is nothing else than a small distance in x. So if I was going to take this and I take a small particle and I call this x, I call this y. So that small particle, what's going to happen is it's going to have two components. Okay, if I zoom this out here, zoom this out here, this component looks like this. Is a small infinitesimal element in x, also small infinitesimally distance in y. Now, however, when that's moving, the velocity change related to that is v, because it's in the in this y direction, and the velocity here is u because it's in the u direction. Okay, so if I said this is actually a function of time, right? I can say I can have this ratio, then my total velocity is v over u, right? Because if I would like to have this angle here, right, and if I take the tangent of theta is nothing else than v over u, where v is nothing else than dy dt, the time of change, right? Time of change of x. And then if I can, don't tell mathematicians I told you this. They will hate us, but we engineers, so we don't care. We can cancel this out, and that's how you end up with dy dx. Okay? And so another thing that you can possibly think of is the following. So in steady flows, streamlines don't change with time. It makes sense, right? Because it's time independent. I talked about that in last class. Unsteady flows, on the other hand, the streamlines do change with time. Okay, that's important to keep that in mind at every single time. So if I had, as for an example, I had a steady flow. Let me give you an example of a steady flow. Steady flow, your streamline will look something like this. Very nice. So for every point, in every point, this is 90. This is completely horizontal. You have a nice tangential line applied, and in this particular case, the path line is actually the same as the streak line. Okay. Now, for the case of unsteady flow, so when you hit the flow is unsteady, then what you see is you got lots of different path lines. So each path line will have their own, let me change the colors for a moment. So every path line is going to have their own tangential value. They don't have to actually follow the same value. And that's why when you draw this and the streak lines, as you can see, streak lines don't necessarily follow they're not equal to the path line. Okay. So what I want to do is I want to do one example right now here in this particular lecture. And then I will leave you with another example, a couple examples in a separate video.